Okay, and before I begin, I want to thank Oriel College and especially Bill Wood for the wonderful hospitality I have received here while in Oxford. It has been really a wonderful experience and a great pleasure, and I have benefited as a person and as a philosopher very much by this. So, let me start with an argument I'm not going to be pursuing, but it's kind of there in the background as sort of in the historical background. So Descartes in the third meditation says this: I clearly understand that there's more reality in an infinite substance than in a finite one, and hence that my perception of the infinite, that is God, is in some way prior to my perception of the finite, that is myself. Whenever I know that I doubt something or want something, I understand that I lack something and am therefore not wholly perfect. How could I grasp this unless I had an idea of a more perfect being that enabled me to recognize my own defects by comparison? So Descartes thinks that we get our concept of the finite from the concept of the infinite. And this is a talk on where we get our concept of the finite from, but it is not Descartes' argument, because Descartes has a different notion of the finite. Descartes is working with this more etymological notion of the finite as what is incomplete, what falls short of something. That is not the sense I'm interested in. I'm interested in the mathematical sense, in which we say there are infinitely many prime numbers. But of course the prime numbers do fall short. They fall short of the other numbers. There are plenty of numbers that are not prime numbers. So they're not infinite in the Cartesian sense of lacking nothing. The set of prime numbers lacks the number 1 or the number 8 or pi. So I want to talk about something a little bit different than Descartes' thing, though maybe there's some connection that I don't see, but I don't see a direct connection. I'm interested in the mathematically finite and whether there's an argument for the existence of God from that concept. So let me start with this puzzle that I've been wondering about for a while, about proofs. So a logical proof seems to be this: a sequence of statements, each of which is either a premise or an axiom or a consequence of what came before in the proof. That seems right, sounds right. Except here's a counterexample. We give an infinite proof. We start by speaking from eternity, ... At step -3, we say roses stink and roses stink, from which we conclude that roses stink by conjunction elimination, from which we conclude that roses stink and roses stink by conjunction introduction, and then we conclude again that roses stink. And we've been going through this alternation between roses stink and roses stink and roses stink for eternity. Each step in this proof does indeed follow by the established rules of logic from the preceding ones, or is an axiom. Well, actually none of them is an axiom, so that's trivial. So each of them just follows from the preceding ones. And so we've proved that roses stink, which is false. And so something's wrong here. And the point is this, is that this seemingly good definition of a proof is missing a crucial qualification, that we are talking about finite sequences, and I'll add also of finite statements. We need that additional qualification, or else we let in some things that really shouldn't be proofs. How do we tell that they really shouldn't be proofs? Well, because they prove things that aren't so, without any assumptions. If you prove something without any assumptions, it had better be unconditionally true. Okay, so this suggests that in some way the concept of the finite has to come before logic. It has to get this idea of proof off the ground, we have to have some way of recognizing the finite. So what do mathematicians do? Here's the standard mathematical characterization of the finite is this. We say that a set is finite, provided that you can number its elements, 1, 2, 3, and so on, up to n, for some natural number n. So a finite set is one you can put into one-to-one correspondence with the numbers up to something. Yes, but then we want to know what a natural number is. And we better not include infinite ones, or else we have a poor characterization of the finite. So to characterize the finite, it seems we need to characterize the natural numbers, 0, 1, 2, 3, and so on. And we need to distinguish them from infinite numbers, which we can actually make some mathematical sense of. There are ways of dealing with them. So the most natural approach in Western thought to these kinds of things, starting with Euclid and so on, is to go axiomatically. Let's come up with some axioms that the natural numbers satisfy. And the standard story is we go for the piano axioms, and they will include they will have this special operation called the successor operation. I write it here as S. The successor of n is just n plus 1. And then they have a bunch of axioms about the successor operation that are, most of which are pretty intuitive, like the successor of n isn't the same as n, that every number other than 0 is a successor of some number, and a whole bunch of others, including a rather complicated axiom schema of induction, which is not going to matter much. The details are not going to matter for this talk. It turns out there are actually infinitely many axioms. That's okay, because when we give a proof, we don't have to list all the axioms. We just need as many as we need. That's fine. We also assume that the piano axioms are consistent, which is something that typically we say we can't prove. That's fine. They seem so intuitive. They should be not just consistent, but true. And if they're true, they're consistent. So that's okay. And if we say, all right, so a proof has to have a finite number of steps, and finite means we can number them with the numbers, and then we say the numbers are characterized by this set of axioms that will, in fact, rule out the Rose's think argument. For one, you can just see the numbers are supposed to be generated with a starting number, always, and there isn't a starting step in the proof. So if you try to number this with the natural numbers, you can't. You can only number it with the negative numbers, in fact, here. So if we try to number with the natural numbers, we won't be able to do it. So we can rule out the Rose's think argument. So that's nice. That's a start. But we still have some problems. So here's just a little warm-up to suggest why we might have some problems. Let's say I try to prove to you that 2 is finite. And that just means 2 is a natural number here. So because we're thinking of the finite as what is numbered by the natural numbers. So by definition, what is 2? 2 is the successor of the successor of 0. It's the number that comes after the number that comes after 0. Hope I didn't get an extra successor in there. Okay, so let's try to prove that it's a natural number by using the standard axiom. So here's how we do this. We apply an axiom. We get that 0 is a natural number. Okay, good. That's an axiom. We have another axiom that says that for any natural number n, its successor is a natural number. Okay. Special case of number 2 is that if 0 is a natural number, then its successor is a natural number. Okay. Special case of an axiom that follows from the axiom. Good, that follows. So therefore, the successor of 0 is a natural number because the antecedent is true. 0 is a natural number. Good. So the successor of 0 is a natural number. If the successor of 0 is a natural number, the successor of the successor of 0 is a natural number. We get that by just plugging in S0 for n into this axiom. Good. So the successor of 0 is a natural number. And we've proved that 2 is a natural number and hence finite. That sounds great until we realize that it's taken us 4 non-axiom steps to do this. And we are worried, and the reason we started worrying about what is finite was because we are worried, how do we know that we're dealing with finite proofs? So it seems like to prove that 2 is finite, We use a proof that has 4 non-axiomatic steps, and it seems like to know that that's a good proof, we need to know that 4 is a natural number. So to know that 2 is a natural number, we need to know that 4 is. And that is not leading us to a good place, right? To use the same method of proof to show that 4 is a natural number will take 8 non-axiomatic steps, and so on. That is not actually a very serious problem, I think, because we can modify the axioms if we want to make this work better. We can add some extra axioms that nobody will dispute. Add the axioms that the successor of 0 is a natural number. That saves us 1 step in the proof. Add the axiom that the successor of 0 is a natural number. Now that 2 is a natural number becomes an axiom. That's easy to prove. You can get it in 1 step. And then for convenience to make these proofs go really fast, we can say that for any natural number, 3 plus that number is natural. That lets us just, if we want to prove that 100 is a natural number, now we get to count by 3s up from 0, and that goes a lot faster. And now we can do the proof in much fewer steps. In fact, 2n divided by 3 steps proves that n is a natural number. And so we can now do this without this vicious regress where our proof is longer than the number that we're trying to prove to be finite. We no longer have that if we add these extra axioms. And of course, anybody who bought the original axioms is going to have no trouble with these axioms. So we can get around that little cutesy argument that there is a regress, a vicious regress. But I think there's still a serious problem. And I wanted to give you that little regress just to problematize this question of how we know that a given number is finite. And the deep problem here is that the axioms of arithmetic, that's these piano axioms like that 0 is a natural number and the successor of a natural number is a natural number and so on. They have what people call non-standard models. These are mathematical structures that fully satisfy the axioms, but include what from our point of view are infinite numbers. And you can just prove that these things exist, at least given some set theoretic assumptions that most mathematicians accept. So we can get these non-standard models of the naturals. They will include the naturals as a little part of them, and then it will go on to add infinite natural numbers, and they will fit with the axioms. Unfortunately, once you have these non-standard naturals that include infinite numbers, you can get infinite proofs where the steps are numbered of the non-standard natural numbers. The parts of each statement are numbered of the non-standard natural numbers, and they sound like but these non-standard natural numbers that include infinite things satisfy all the same axioms. So we can't just rule them out by saying, well, we've got these, like we can rule out the roses stink argument by saying, well, that didn't have a first step, and the natural numbers must have a first one. These non-standard ones, they do have a first one. It's 0, and they go on through all the normal ones, and then they go on even further and further and further. So we've got a problem. We can still give infinite proofs. This leads to a couple of different kinds of philosophical worries. One is a semantic worry. How is it that our language of finite or number, or natural number to be precise, gets reference to the ones to the correct ones, to the standard model, not the non-standard model, to the one that actually we're intuitively thinking of. This is the sort of what people call the Kripkenstein kinds of worries. Kripke and Wittgenstein had similar worries about other kinds of closely related, but other things. And then we can ask more skeptical questions. How do we know that our natural numbers, what do I mean by ours? Well, things like 0, 1, 2, 3, 4, 5, 6, 7, 8, a billion, a trillion. How do we know that those are not non-standard from the right point of view? How do we know that what we call standard proofs, ordinary proofs, are not actually non-standard from some other more expansive point of view? How do we know that we can trust our proofs? How do we know that they are actually finite? given, yes, so we can give these kinds of proofs that 4 is finite or that 100 is finite once we add these axioms, and the proofs will be non-circular. But within a non-standard model, you could do the same story. You could give the same kinds of proofs. They'll just be infinitely long, but they'll sound like they're finite from the point of view of these infinite numbers. How do we know? Well, this is a deep kind of puzzle. And there's a question whether it matters. And I think it matters a great deal. So you might have an initial hope that it won't matter. That, yeah, so maybe you can allow these infinite proofs, but we've already said we're not going to get a proof like the roses stink one because every proof has to have a starting point because the natural numbers have to start somewhere. So maybe we're just going to get nothing really bad provable. Maybe, one of the things we can prove now, if we've got infinite proofs, we can be able to prove some perfectly innocent things, like an infinite conjunction of true statements like 0 equals 0. Okay, not a big deal. We can prove that, and it's true. That's perfectly fine. Unfortunately, it's not all hunky-dory. Gödel's second incompleteness theorem tells us that assuming that arithmetic is consistent, there is going to be a non-standard model such that if you allow proofs where the statements are numbered with the non-standard natural numbers in that model and the parts of the statement are numbered with them, then you can get a proof of an inconsistency, of a contradiction from the axioms of arithmetic. So one of those things that you can prove using these infinitely long proofs is actually that the axioms of arithmetic are inconsistent. But we think they're true. They're so obvious. And they can't be inconsistent and true. So it means that we can actually disprove the axioms of arithmetic using an appropriate non-standard model. And that's bad. So it's not just an innocent expansion of what we can prove. It's an expansion that allows us to prove stuff that just isn't so. Moreover, if we allow infinite proofs of the right or the wrong sort, there will be perfectly normal finite sentences you could just write down, which are consistent according to standard methods of proof. But when you allow infinite proofs, you get contradictions from them, from normal, single, finite statements. And so that means that what is and isn't consistent depends on what kinds of numbers you allow for the numbering of the statements in the proofs. Where if you allow these infinite things, these weird infinite numbers, you get to prove that some things are inconsistent that probably are not inconsistent but are consistent. This isn't how logic should be. Now, a naive move might be to say, well, okay, here we said you get these non-standard bits of kinds of arithmetic with these infinite numbers that match the piano axioms of arithmetic. So you might think, well, okay, maybe we should just add some axioms to rule them out. And you can do that to some degree. Any particular thing we don't like that we get out of these infinite numbers, we can add an axiom that rules out that particular pathology. We can add an axiom that will rule out the proof of the inconsistency of the piano axioms, say. Unfortunately, however many such axioms we add, there will be other things which will suffer from exactly the same problem. So we will always, just adding axioms will not get us out of this problem. So we've got this problem that the notion of proof depends on the notion of the finite. The standard way to understand the finite is in terms of what you can number with the natural numbers. But there are perfectly logically coherent sets that have an operation that functions like the successor operation that satisfies the same axioms, but such that if we number our proofs and the elements in them with those numbers in the steps, we are going to be able to prove stuff that isn't so. So it means we need to have some other way of finding a concept of the finite to get a concept of proof. And the concept of proof seems central to logic. And logic, while it's not the only tool that is used in our knowledge of the world, is at least a central tool. If we can prove something with logic, we think it's got to be true. So we need some sort of a characterization of the finite that rules out infinite proofs to save logic. So what are we going to do? Well, I'm going to consider 4 different solutions. One of them uses physics, one uses metaphysics of a particular sort, metaphysics of modality, one uses God directly, and the last one uses a speculative theory that I've been defending recently called causal finitism, which also leads to God. So it'll turn out that of the 4 solutions I will consider, 2 of them have some kind of connection with God. And the 2 solutions that don't, I think, are incomplete unless something is said that I think also leads to God. So let me consider 2 solutions first that don't involve God in any way. Start with physics. So here's one thing. You can't write down an infinite proof. Why? Well, because it would take infinitely long. And so you'd never be done. Well, could you maybe do it like in some kind of really fast way? You write down the first step in a minute, the second step in half a minute, the third step in a quarter of a minute, and so maybe in 2 minutes you'll be done writing down infinitely many steps? No, you can't, because then your hand will be moving faster than the speed of light eventually as it's writing to cover, this length of page, right, with in the amount of time that's getting shorter and shorter and shorter. And could you write smaller and smaller? No, you can't, because ink's made out of atoms, and you need a minimum number of atoms to actually be able to make a letter out of them. So there is a physical limit that ensures that we physically could not write down an infinite proof. So, hey, we are lucky we can't write down any infinite proofs, so we're not going to write down any of these bad proofs. So maybe we could say, hey, here, in the spirit, the finite is what we can actually finish counting, say at 1 item a second. And we can't just accelerate our counting faster and faster, because then our mouths would be moving faster than the speed of light. And the pitch would go ultrasonic pretty quickly too, and so no one would hear us. So physics maybe comes to the rescue here and rules out these proofs. There are some problems with the physics answer. First of all, it seems intuitively odd that logic should depend on physics. And specifically on modern relativistic physics, which has that speed of light limit. That's strange. Okay, but strange things are true. Many strange things are true. Here's another thing. If we really insist on the physics thing, then it means that what really is provable, if physics defines the provable, then what's provable not only depends on what's finite, but on how much time there is. What if physics says that time is finite, that time has to come to an end? That means that some things that, in fact, I guess if the numbers are the ones you can actually count physically, there are only finitely many numbers. That seems bad. Here's another problem. Physics, all the equations of physics could be interpreted in a non-standard model of arithmetic that has infinite numbers in it. And you have the speed of light limit and all that stuff there, and you can still have an infinite amount of time pass by, because that infinite amount of time will actually behave just like a finite number as far as the axioms go. You could have a physics that is just like our physics, has exactly the same mathematics, but that involves infinite quantities. So how do we know that we're not in that boat? How do we know that our physics isn't that kind of infinite physics with infinite lives? How do we know that what the physicists call a finite number of seconds is really finite? What if it, okay, maybe it is. Suppose we get lucky and our physics is in fact, what physics says is finite is in fact finite. Why is that? How do we get so lucky that our physics matches proofs and what is needed for proofs to work? That seems weird. But at least the physics story is that it says that if we get so lucky that the things that physics says are finite are in fact finite, then at least we have a solution to the semantic problem of how we know, of how we can, our language of the finite makes sense because it gets its sense from the physics. So we can at least, we can't solve the skepticism worries, how we know this stuff worries, but we can solve this problem of the semantic Kripkenstein problem maybe by saying the natural numbers are like times, say, that physics talks about. So it's a partial solution, but not a complete one. Maybe we can use metaphysics, the metaphysics of modality. So we have this notion of metaphysical possibility and metaphysical necessity, which isn't just logical. So it'll include things like it's metaphysically impossible for something to cause itself. There's no logical self-contradiction. You can write down a theory in which something causes itself, but it's just metaphysically impossible, or it's metaphysically necessary that every horse be a mammal. Again, there's not a logical proof you can give of that, but it's just impossible. It just couldn't be a horse if it weren't a mammal. So we have this notion of what's metaphysically necessary and metaphysically impossible and metaphysically possible. And we can try to give now an account of logic in terms of that. So here's one way to do this. We say that some sentence is, I'll call it M contradictory, provided that that sentence is metaphysically impossible no matter how you interpret the names and predicates in that sentence. So it would be impossible to interpret the names and predicates in the sentence in such a way that the thing would be true. Okay, that works. I mean, you can say that. And then you could say, now a model of arithmetic is M acceptable, M for metaphysically, provided that the sentences that are logically contradictory according to that model, namely the ones from which you can derive a contradiction where the proof is numbered by the numbers in that model, are in fact metaphysically contradictory, and vice versa. So we could say the good models of arithmetic, the good sets of natural numbers, are the ones that match metaphysical contradictoriness correctly. We could then say a proof is metaphysically acceptable provided that it is valid according to a metaphysically acceptable model of arithmetic. And again, I think we get a solution to a semantic problem. How we can refer to one particular collection of mathematical objects as the natural numbers. We can, maybe not one particular one, but we can at least specify that we are interested in those models of the natural numbers such that if we number proofs with it, they match the notion of metaphysical proofs, the things that follow no matter what interpretation of names and predicates we give. So we get a bit of solution part of the way. If we want to go further, we need an account of metaphysical possibility that does not depend on purely logical possibility. That actually rules out a number of the theories in the metaphysics literature, because a lot of the theories of metaphysical possibility depend on what can be proved and what can't be proved. And here we're using the metaphysics prior. And some of these accounts of metaphysical possibility may yield arguments for theism, like my favorite account in terms of causal possibility does. But not all of them will. So there's ways forward here. I think we still have an explanatory question. Why is it? This is a very strange explanatory question. but why is it that we're so lucky as to live in a world where our physical proofs match the metaphysically acceptable ones? There's nothing contradictory about a world which has at least Darwinism doesn't seem to be, as far as we have it right now, there seems to be nothing contradictory about a world which has an infinite future such that there will actually be times that are infinite, that we can go beyond, and those times match the laws of arithmetic, and we can, if we given those infinite amount of time, we could actually physically give proofs of things that are false. But we think that's not the case. We hope that's not the case. If it is the case, our logic is in trouble because we can physically give proofs that don't work. So why is it that our physical proofs match the ones that are actually metaphysically acceptable? And how do we know that we are so lucky? So why are we so lucky, and how do we know that we're so lucky? So again, the metaphysical story, I think, helps, but it doesn't solve the whole problem. So I want to try two other things. One is an old one. It goes back to St. Augustine. So St. Augustine famously thought that mathematics was all grounded in ideas in the mind of God. Or you could have a variant of it that I think Thomas Aquinas would probably agree with, that mathematics is grounded in God's power. In any case, it is grounded in something in God. And if it's grounded in God, then by introspection, God has direct access to all of mathematics. And he can choose a particular model of arithmetic, a particular collection of things that behave like the natural numbers, that just fits with what he wants, namely with truth and proof that leads to truth. And God can then ensure that our words, finite or number, match up with the model of arithmetic that God has in mind that fits with the notion of proof. He can do this in multiple ways. One way he could do it is by ensuring we have a human nature with certain semantic properties that ensure that our words have certain meanings and that they have this meaning. Or he could let us get the meaning of the words by semantic inheritance from God. Namely, one way of the ways we get meaning, our words get meaning, is we talk to other people who know what they're talking about, and we get to use the same words as they did, even without understanding them very well. So the ordinary person uses the word electron by some kind of semantic inheritance from scientists. They have no idea what electrons really are. Maybe, I don't know how much idea the scientist has either, but they have hopefully a better idea at least. So you can inherit the meaning of the word electron. You can be a 6-year-old talking about electrons and making sense, and your words have meaning because as a 6-year-old you've inherited, not directly, but typically through a chain of inheritance, say from your parents, and they from a teacher maybe, and they from a scientist or something, the meaning of the word. Well, God could also enlighten the mind of some philosopher or mathematician thinking about the finite, and in such a way that that person uses the word finite or number in accordance with what God means for that number to mean. And so the meaning of the word as used by them is inherited from God. So that's one option. God could just make sure that our words match what he wants, the particular structure of natural numbers. The other option could be, we could take the physics way out and add God to it and say, God can ensure that the physical world's time sequence and laws of nature and the physical possibilities for proof formation do in fact match the correct notion of proof. That time isn't non-standard in such a way that we could give non-standard proofs. And maybe we could say, if we believed in God, we could say God is likely to do this in order that we might be able to employ logic. So theism can fill out the physics and metaphysical possibility answers by answering some of these questions that they left unanswered, which is, why is it that we have this match between the physical proofs that we can give and the ones that actually work, that are really, truly finite. So it fills it out. As a bonus, if we have an account of mathematics as grounded in the mind of God or in God's power, and we have the story that I gave in the first Wilde lecture of beauty as participation in God, it's not surprising that mathematics is beautiful. So we get an explanation of something, a completely different question, why mathematics is in fact so beautiful, which is a very interesting question as a little bonus. Okay, so that's one approach. One way to define the finite is saying, well, God gets to define it and we get it from God. Here's a different approach. This approach uses some paradoxes of infinity. I actually don't think the first one's much of a paradox, but it's so easy to understand that I want to give it as a warm-up. So this is called Thomson's lamp. Philosopher Thomson, middle of the 20th century, came up with this. And the idea is this. We've got a lamp. Ideally, this would be a push screen, so if I could push it, the lamp would turn on and off each time I pushed it. Couldn't set things up that well. So you just have to imagine it. And so the lamp starts, each time it's pushed, it turns on or off, depending on whether it is off or on. It starts, the thick lines are where it's on, the thin lines are where it's off. So before 10 a.m., the lamp is off. At 10 a.m., the button is pressed, the lamp turns off. Then at 10:30, it's pushed again, it turns on. At 10:45, it's pushed again. Okay, so now it turns off. At 10:52.5, it's pushed again, turns on, and off, and on, and off, and on, and off. And then the question is, it's pushed infinitely many times, each time cutting the remaining time in half. At 11 o'clock, is it on or off? And as my son said when I told him this paradox the first time, he said, it depends on whether infinity is even or odd. But of course, infinity is, in some sense, neither even nor odd. Maybe in every sense, neither even nor odd. So it seems like there's no answer, but there should be an answer. You should be able to do this experiment and see. Now, there are standard stories about this one. I think some of the standard stories work. One of those is just, there's no contradiction here. It just says we don't know what the answer is going to be if you do it. Maybe it's undetermined what it will be. Maybe this is an instance of indeterminism. It's still a little surprising because it seems like this is a perfectly deterministic, should be a perfectly deterministic system, and yet we've got an undetermined answer. I don't know. I don't know what, maybe it's a violation of the principle of sufficient reason, you might worry. I don't know. I'm not very worried about this as a paradox, but it's a really nice little story that's fun and easy to visualize. The one that worries me more is the Grim Reaper paradox, which comes from Bernardette's wall paradox, again, sort of mid-20th century. And the idea is this. We've got two kinds of beings, Fred and Grim Reapers. This picture has only one Grim Reaper, but there are many of them. And each Grim Reaper is armed with a vicious weapon and very sharp. And each Grim Reaper, it's not shown in the picture, has an alarm clock. And the Grim Reaper has an alarm clock is set for a particular time. When that clock goes off, the Grim Reaper wakes up. See, they all start off as asleep before 10 a.m. And when the Grim Reaper's clock goes off, the Grim Reaper wakes up, looks at Fred, and checks whether Fred is alive or dead. Which turns out to be very easy because the only way for Fred to die in this scenario, it is stipulated, is by having his head cut off. And so it's easy to tell whether he's alive or dead by checking whether his head is on his shoulders. So the Reaper looks and checks whether Fred is alive or dead. If Fred is alive, the Reaper does nothing and goes back to sleep, merely observes. If Fred is dead, the Reaper does nothing. Says, my job has been already done. I don't need to do anything. I am a head cutter. The head is off. All is well. But if Fred is alive, then the Reaper instantly cuts off the head. You can make it, it doesn't have to be absolutely instant, but just easier to tell the story that way. And then the Reaper goes back to sleep. Okay, we stipulate some things. There's nothing here that can kill, there's nothing else that was going to kill Fred in the vicinity. Fred is alive at 10. And we also stipulate that if there is a resurrection of the dead, it doesn't happen between 10 and 11 a.m. Okay, so now we suppose, this seems perfectly coherent to have such a Reaper. It also seems coherent to have infinitely many such Reapers with their alarm clocks set for different times. Except now let's imagine that one Reaper has their alarm clock set for 10:30, another for 10:15, another for 10:07.5, and so on, cutting each time in half. So we've got infinitely many Grim Reapers. Each of them has their alarm clock set for some time between 10 and 11. So now we can ask what happens to Fred. Well, Fred cannot possibly be alive at 11, because if he were alive at 10:30, that Reaper would have killed him. So he must be dead at 11. In fact, he must be dead right after 10:30. Could he be alive at 10:30? No, because the 10:15 Reaper would have cut off his head if he were alive or any earlier. So he has to be he has to already be dead here. Notice that the fact that he's already dead here and dead here means that these Reapers did nothing. They just woke up and saw. Okay, so maybe this one did nothing. Maybe this one did something. No, because this Reaper would only have reacted if he was alive, but this one would have killed him already if he was alive before that. So in fact, you think about it, none of the Reapers could have killed Fred. Because to have killed him, the previous Reaper would have to have fallen down on its job. And it is part of the suppositions of this story that they don't fall down on their job. So on the one hand, Fred is dead at 11. He has to be dead. There's so many Reapers, each of which is sufficient to ensure his death. And on the other hand, none of them do anything but observe. John Hawthorne has suggested that maybe the mereological sum, that the sum of all of these Reapers together kills him. Now, granted, seeing an infinite number of Grim Reapers could scare one to death. But we have supposed that the only mode of killing is by cutting off heads. And when none of them swing their scythe, even all together, they do nothing. So there's a puzzle. He's alive. Here, he's alive at 10, dead at 11, nothing killed him. Problem. Third puzzle. Let me start with this odd supposition, and then tell you how I could get this odd supposition, or you can see it if you read ahead. So imagine I have an infinite deck of cards. Here, very long, it goes all the way down. It numbered 1, 2, 3, but it's shuffled, so they're not in order. They are in fact shuffled very, very well. And now I'm going to show you that you can get some very strange stuff in this infinite well-shuffled deck. So let's say you and I play this game where we each draw a card from the top of the deck, and the one who gets the bigger number wins. I look at my number, and it says 10 to the power, 10 to the power, 10 to the power 10. That's really big. And I think, good. But then I think a bit more. But wait, there are only finitely many numbers smaller than this one, and infinitely many bigger than that one. So you're way more likely to have one of the bigger ones. In fact, it's infinity to a finite number that you have one of the bigger ones. So I'm going to now think, I must have lost the game. You look at your number, which is probably something also extremely large, and you make exactly the same inference, that Alex's number has got to be bigger, because after all, there are only finitely many that are smaller and infinitely many that are bigger, and the deck has been shuffled quite well. So we each despair of our card, and so we swap. And we're each happy with our swap until we see the card. There's something wrong here. There's something wrong about the fact that we would be both willing to swap. There's something paradoxical here about the fact that we will be both sure that we've lost no matter what. And in fact, even before we drew our card, we already knew that as soon as we see our card, we will despair, no matter what it is. We can be like sure of despair. And we'd be happy to trade. In fact, so why wouldn't we just agree to trade ahead of time? But that would make no sense at all. Because after all, it should be 50-50 who gets the bigger one if it's a well-shuffled deck. So this is very strange. Second fun version of this is I take the deck and I draw 100 cards and just put them down side by side. After each card I draw, I expect the next one will be bigger. How strongly do I expect it? About infinity to a finite number. So I'm nearly certain that the next one will be bigger. Because again, there are finitely many that are smaller and infinitely many that are bigger. In fact, I expect not only that the next one will be bigger than the current card, it'll be bigger than all the cards I have already drawn. So at each step, as I keep on drawing cards from this infinite deck, I expect that the next one will be bigger than all the previous ones. And I'm nearly certain, infinity to a finite number, which is basically the same as infinity to 1. I will bet anything on the next one being bigger. Okay, so you cleverly agree to take my bets at these odds. You're going to probably do quite well, because surely if I draw 100 cards from a well-shuffled deck, they're not going to be in order. They're not going to go up, 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 up as I draw them. And yet for each one, I perfectly rationally have to think the next one is going to be bigger. There's something really wrong with this expectation. Okay, well, maybe the thought is, yeah, but you can't shuffle an infinite deck. How do you do that? Well, you might try to use an infinite causal process based on an infinite past. Here's, I thought of two processes that might work. I'm not completely sure either of them will be completely fair, but they will be fair enough, I think, to make these arguments go through. So one is on day negative n, I've been shuffling for an infinite amount of time. Maybe I shuffle it once a day, and I've done so for eternity. On day negative n, maybe I had divided the deck into groups of n cards. Say, so 100 days ago, I divided up into groups of 100 cards, and each group of 100 cards I shuffled perfectly in itself, among itself. And so in earlier days, I shuffled greater amounts and greater amounts and greater amounts. Seems like this should result in a really well-shuffled deck. Well enough shuffled it would be, I think, that these arguments should work. Another possibility is maybe I have a bunch of numbered particles, numbered 1, 2, 3, 4, 5, and they move by a random amount in a random direction, randomly either left or right, and they've been doing it for eternity. And since they're numbered, I can then take a starting point, some fixed point, and just look at their numbers as we look from that fixed point. So we look at the closest particle to me, take the number from that. That'll be the first card on the deck. Then the next particle, its number will be the next one. Then the next particle, its number will be the next one. Should be able to do stuff like that. Okay, I don't know. I think there's actually some technical problem with this version. But you can make these technical problems go away and get this story where you have shuffled this deck if you are allowed to do an infinite number of shuffles of some sort. And then you get these weird paradoxes. So we've got these weird paradoxes. We've got Thomson's lamp, which maybe isn't too bad. We've got the Grim Reapers, we've got the infinite deck, and there's a whole bunch more. Of a somewhat similar variety, but somewhat different in each one. But all of them involve a common feature. We've done infinitely many things. Well, how are we going to get rid of these paradoxes? Well, one way is just to say, well, which one is a paradoxical, so you can't have paradoxical things. It's not very satisfying. There seems to be that a lot of these, the three stories I gave you and the other ones that I have in this book on infinity, causation, paradox, they all have a similar structure. They involve an infinite number of causal interactions, like shufflings or Grim Reaper's ensuring death, or button pressings. We could try to rule out such paradoxes by being strict finitists. Just say there's no such thing as infinities. You can't have an infinite number of anything. That rules out all these paradoxes, at least given some extra theories, some extra statements about the theory of time. Unfortunately, that conflicts with mathematics, at least prima facie, because mathematics says things like there are infinitely many prime numbers. What I want to go for, what seems to me to be what I think is the best explanation of what goes wrong in a lot of these paradoxes, in all of these paradoxes, in fact, is that they involve an infinite number of causes impacting in some way, ensuring, affecting a single event. And I say, my theory is that that's not possible, and I call it causal finitism. It's not possible for infinitely many causes to affect a single event. And this solves this and similar paradoxes. So we've got some, if we want to get out of these paradoxes, we've got some reason to adopt causal finitism. Here's another. So it's a simple principle, rules out many paradoxes. It allows for non-causal infinites, just as mathematics requires. Mathematics doesn't require causal infinities because mathematics doesn't talk about causation. It talks just about how things are, not what they do. So we have some reason to accept this theory is true. And if we accept this theory is true, we can give a different metaphysical account of the finite. So here's one, and of proof. There are, let's call it genuine finiteness. So we say there are genuinely finitely many of something, provided that it will be possible to think of them in a causal sequence. What do I mean by that? I mean, you think of one, then you think of the next one because you've already thought of the previous one. Then you think of the next one because you thought of the previous one. And you think of the next one because you thought of the previous one. I mean, that's normally what we're doing when we're counting, right? I count my fingers, 1, 2, 3, 4, 5. Actually seemed to come to 6. I don't know why. But anyway, as I count them, except for the first one, each one I say 2 because I said 1. I say 3 because I said 2. And I've got some kind of causal process going on in my brain where my saying each number is caused by the previous one and some kind of habit I've got of counting. You could do this with thinking as well. And that's what I mean by thinking of them in a causal sequence. But if causal finitism is true, this is guaranteed it's guaranteed that if it is possible to think of a bunch of things in a causal sequence like that, then there must be finitely many. Starting with one and leading to a last one. Because if there were infinitely many, then my saying the number of the last one would have infinitely many causes. All the preceding numbers that I have said. So if causal finitism is true, then this technique of going through them one by one with there being a last one is guaranteed to only work if there are finitely many. Nice. So I have an account of the finite, maybe. I have an account of what I call a causal proof. A causal proof is one where it's not just that each step logically follows from the previous ones, but that you only wrote down each step or said it or thought it because of the previous steps, except for the first one. So that's a causal proof. Each step is your thinking or saying or writing each step is caused by your thinking, saying, or writing the previous step. That's a causal proof. And if causal finitism is true, if things can have only finite causal histories, then causal proofs have to be finite. So the metaphysics of causation on causal finitism gives us an account of the finite and of what genuine proofs are, causal proofs. And then we could say a genuine proof is one that you could realize causally. So the metaphysics of causal finitism could pick out the true notion of the finite. And once we have a notion of the finite, that gives us the natural numbers, and so we can give natural numbers. Moreover, because physics is causal in nature, if you can have only finitely many causes of a thing, you can only have finitely many physical causes of a thing, and you get and physical proofs have to fit with this story, and physical proofs have to be genuinely finite as well. So it solves the luck problem of the physics approach. It's not just luck. Any causal story, no matter what kind of physical causation we would have, would not allow us to do an infinite proof. So that is nice. What's that got to do with God? This is natural theology, not philosophy of mathematics per se. Well, causal finitism has another corollary, or bonus as you might call it. It underwrites a version of the Kalam cosmological argument for a first cause. The Kalam argument goes something like this. Here's one version of it. Something causes something. Uncontroversial claim, pretty much. A few Humean philosophers may dispute it, but it's generally uncontroversial. Second, highly controversial premise. There's no infinite regress of causes. Third premise, fairly uncontroversial. A few people, like Quentin Smith, maybe some physicists who think maybe time goes in a circle, but may dispute it, but generally undisputed that there's no circularity of causes. 4, it follows that there's an uncaused cause. Right? Something causes something. There's no, well, either that's uncaused or there's a previous cause. And we can't go in a circle, we can't go to infinity, so we must stop somewhere. So this argument is valid. The conclusion follows from the 3 premises. The most controversial premise is there's no infinite regress of causes. But that is precisely what causal finitism ensures, because an infinite regress of causes would mean infinitely many things having as their causal upshot one final effect, or at least affecting it in some way. So an infinite regress of causes is ruled out by causal finitism, and so we get an argument for an uncaused cause. Of course, after this would come investigation of whether the uncaused cause is God. Maybe here we get Aquinas' metaphysics of uncaused causes. In the Summa, we get maybe can give design arguments. Maybe the arguments of the previous talks can be combined with it. Some work is needed to go from an uncaused cause to God, but we at least move in that direction. So here's the story we had today. We need an account of the finite for logic to work. We can't just do it axiomatically, because we can't just axiomatize the finite, because we will still always have non-standard models, as long as our axioms are consistent. We can give a physics account of the finite, but it suffers from luck and skepticism problems. We can get a metaphysical necessity account, but also suffers from luck and skepticism problems. We can give it a theistic account, along the lines of Augustine, or maybe Aquinas, in which mathematics is grounded in the mind of God, and God, in some sense, reveals the natural numbers to us or to somebody that we have inherited the concept from. And as a bonus, we get an explanation of the beauty of mathematics, because if God exists, presumably he's all beautiful, and mathematics is about him. The other solution that does also seem to do a job is we get out of a whole bunch of thorny paradoxes by embracing causal finitism, which also solves the luck and skepticism problems without invoking God, but at the same time underwriting the most controversial premise of the Kalam cosmological argument for the existence of God. Thank you.